Let's see today another topic for physical design of analog VLSI, that is to use the Euler rule for the physical design. Now in this lecture we will see what actually the Euler rule is and why we implement this rule for the physical design and how we will use the Euler rule for the layout design for the CMOS circuits, okay, and what are its benefits. So before I start, let us see what actually the Euler rule is. In any given circuit, the Euler path is that path which transfers every edge exactly once and only once. Okay, so for a given circuit there are number of paths available. So the path that travels through all the edges, and but it should travel only once, okay, and the vertex can be repeated but the edges cannot be repeated, okay. So for any circuit, if we have such kind of path in it, that is known as the Euler circuit, okay. That circuit is known as Euler circuit if it has the Euler path. Now we have the closed loop circuits, and in the closed loop circuit the starting node and the end node is the same for the closed loop, okay. So similarly here, that in the Euler circuit the first and the last vertex are same, okay. So basically Euler is a mathematical term that is used for various applications, and we will now see the application of this Euler rule in designing the layout of our VLSI circuits, right? So that circuits consist of the transistors NMOS and the PMOS, okay. Now let us understand more about the Euler path with the help of this example. In this example, a closed circuit is shown here. Then the circuit is consists of the four vertices 1, 2, 3, 4. Okay, the named as vertices 1, 2, 3, and 4. Now in the circuitry, our purpose is to look out the Euler path, right? So from the definition, the Euler path says that it transfers from all the edges, okay, but only once, okay. It covers all the edges and but only once, right? So let us see here the Euler path. The arrow shows the how we proceed, and we consider the vertex 1 as a start vertex, and from this vertex we proceed to 2, vertex 2, then to vertex 3, then to 4, and finally to again vertex 1, okay. So in this case we will see that the Euler path is 1 to 2 to 3 to 4 again to 1. So this will justify the definition of the Euler path, that in a circuit it transfer through all the edges, okay, but only once. Here we see that all the edges are covered in a single way, and the start and the end vertex is the same. So one vertex is your start and end vertex, right? So this will show the Euler path in a circuit. Now we will see that how we are going to use this concept for designing our analog circuitry. Now, okay. Now to understand this, let us consider this example, that we are consider here a NOR circuit which consists of two PMOS connected in series and two NMOS connected in series, right? Now if we want to implement it, then I use here the stick diagram to show the layout actually. Then it is seen here that the PMOS diffusion shown with the yellow line on the upper side and green diffusion for NMOS on the lower side. That dotted line That dotted line shows the division of the circuit into the upper half and the lower half. The upper half that is connected to VDD, so that is also known as pull-up circuitry. The lower part that is connected to ground, that is known as the pull-down circuitry. Now what we will observe from here, that I will take you to another side here, that on the upper side two PMOS transistors are connected in series. Okay, the transistor N1 and N2, they are connected in series, both are PMOS. Okay, and if you look at the layout arrangement for this, I have to use here the yellow line rather than the green line. I have to use here the yellow line, right? So let us consider this is a yellow line. So yellow line shows the P diffusion and the red line crosses the yellow line, shows the PMOS transistor. Okay, the main thing you will see that the portion here between the two transistors, this one, this will be shown with a blue line joining the two diffusion. Now here is a major problem area, that two diffusions, they are joined together with a metal contact. Now if we use this metal contact, that will create two kind of problems that the layout design engineer faces. The purpose of the layout design engineer is to make such a design that require minimum area on the wafer. Okay, so that the circuitry will require minimum area on the wafer. And the second aim of the layout design engineer is to minimize the power dissipation. Okay, so that is interrelated. So we should have a little electrical problems, issues, and also the area should be minimized. Now if we join the two diffusion with the metal contact, it will require a large area on the wafer. Okay, so we have number of transistors connected either in series or parallel, and if we go on connecting each diffusion with the metal contact, the overall area required for the circuit construction is more. Now how to reduce this problem or how to overcome this problem? For that we use another concept here that will be shown in the lower portion, that for the two transistors, this portion is a yellow portion because we are considering here a PMOS, so yellow diffusion shows the PMOS. Now this single diffusion layer is shown for both the transistors. Okay, two polysilicones crosses the yellow diffusion area that shows the two transistors N1 and N2. Okay, now look at the difference between the two circuitry here. Here the two diffusion are separated or connected with a metal contact, and here a single layer of diffusion is used for representing the two transistors. That is, the source of one transistor and drain of one second transistor share the same diffusion line. That is the main concern here, that instead of using the metal contact between the two transistors, the same diffusion line share the source of one transistor with the drain of another transistor. The major advantage of using this kind of concept, that is to minimize the metal contact between the circuit. Okay, so if you design the circuitry with this, that will require a minimum area. Okay, and moreover the power dissipation will also be less. Now this is the Euler path concept. What is Euler path concept here? That if you look at here on this side, if you look at here in this circuitry, this path is known as the Euler path. Okay, that the single path, a single path which consists of same same diffusion transistor, that path is known as the Euler path in the circuit. Similarly, if you look at here, the same diffusion path is on the upper side and same diffusion path on the lower side. So our aim is to find out that path in the circuit that involves same kind of diffusion. Okay, and all that transistor will be shown with a single diffusion rather than joining each transistor with the metal contact, right? So that is the major application of the Euler path in the VLSI design. So what is required for the VLSI design using Euler path? That you require a circuit diagram. From that circuit diagram, you first of all trace the Euler path. That is, you first of all trace that path that requires same type of transistor, either NMOS or PMOS, which require same diffusion. Okay, so single diffusion is used for all that transistor rather than the metal contact between the different diffusions, same type of diffusion. Okay, so now let us see another example and let us draw the layout using the Euler path. Okay, right. Now let us consider this example. We have 3 transistors on the upper side and 3 transistors on the lower side, and if I bifurcate the circuitry with the dotted line, the upper portion is pull up and the lower portion is pull down, right? So similarly as we discussed earlier. Now 3 transistor P transistor on the upper side and 3 NMOS transistor on the lower side. So the circuitry is basically the CMOS circuitry, which consists of the complementary transistor. Now we will see the Euler path in the circuit. So let us consider here first the pull down circuitry. So if you start from the ground terminal, then let us take the path from transistor C, then from A to B, and then again to ground, right? So this path transfers through each transistor or edge and reaches again back to same point, that is the ground. So starting from the ground, transfer through each path and then come again back to the ground. So this path is termed as the Euler path in this transistor, right? So that is the Euler path that covers the path as C to A to B. Okay, or it is or you can also draw like this, that you can also draw this Euler path from this F point from C to B to A. Okay, so one and the same thing, either from ground to C to A to B or from C to B to A. The purpose is same, right? So similarly on the upper side, if you consider the Euler path from C to A to B and again come back to this node, right? So this is another path that is on the pull-up side. Okay, so this is also a Euler path. So we have considered the 2 Euler paths, one on the pull-down side and another on the pull-up side. Now the major aim that in this Euler path you will see that the same type of transistors are covered. So for this all the transistors we will take a single diffusion layer rather than the diffusion layer for each transistor and then interconnect them with the metal, right? So for the Euler we will use the same diffusion line for all the transistors that covers in that path, right? So now let us design the layout diagram for the circuitry. Okay, so for that we know for the stick diagram, the blue lines are used for the supply lines, upper for the VDD and lower for the ground. Okay, now upper side we require the P diffusion. So P diffusion is formed with the yellow line, and the N diffusion is shown with the green line. Okay, now this shows the P diffusion and the green shows the N diffusion. Okay, now to form the transistors, 3 PMOS transistor and 3 NMOS transistor, we require 3 polysilicon layers that will cross the N diffusion layer and the P diffusion layer. Okay, so on the upper side you will see the 3 polysilicon layer crosses the same common diffusion line, P diffusion line, and on the lower side the polysilicon layer crosses the same N diffusion line. So 3 PMOS forms on the upper side and 3 NMOS forms on the lower side. Okay, so we will name them with the connection. So this forms the A input. Okay, on upper side this A for the PMOS, and on lower side this A is for the, on the upper side this shows this transistor, and on the lower side this shows the NMOS transistor. Similarly, the B input, on the upper side this will shows the PMOS transistor, B input for that, and on the lower side this shows the B input of this NMOS transistor. Similarly, the third input is C, that is for upper for the C input PMOS and the C input NMOS lower side. Okay, so these are the 3 inputs. Now we know that for the connection, that will be shown with the black line with a cross or a dot. So I have shown here a cross. Right, now the another thing that we remember, that for the PMOS the upper side is source, the upper terminal is source and lower is drain. Upper is source, lower is drain. Upper is source and lower is drain. Similarly, for the N type, upper is drain, lower is source. Upper is drain, lower is source. Upper is drain and lower is source. So we will make that connections on the layout design also. Now how we will design that, how we will write the source and drain for each transistor on the layout, that if you look at here, both the source of input A and B of PMOS transistor, they are joined together and connected to VDD. So we have the transistor A here and B here. Okay, source of both. So let us consider the source as common here. Source and source. Okay, so that means drain is here and drain is here of B. Okay, so source of A and B, they are joined together with the VCC. So that will be shown with the blue line. So let us take a blue line and connect with the source with a cross of black line. Okay, and similarly the cross here. So this will show that source of both the PMOS transistor of input A and B, they are connected together with the VDD. Okay, so one connection is over. Now second, the drain of A and the drain of B, drain of A and drain of B, they are connected together. So again we will take the blue line for the connection. So both the drains are connected together, joined with the black crossing, black cross. So the drain of A and drain of B, they are joined together. Okay, and they will, okay, now next what we will do, come to the lower side of the NMOS. The source of B and C, source of B and C, they are connected to ground. So source of B and C, so that means you will consider the source here and source here. The source of B and C, they are connected to the ground. So take a ground connection here, and they will be joined with the, connected with the cross. Right, so this connection is over. Now the drain of A and C are connected together. So drain of A and C, drain of A and C are connected together. So let us consider drain here. So drain of A and C, they are connected together. Okay, so I have to take here the blue line. So drain of A and C, they are to be connected together. Drain of A and drain of C, they are connected together, and they are connected with the drain of C input PMOS transistor. Okay, so C here, so they are connected like this. Again I have to take here the blue line, so I have to connect like this, joined with the, okay, so drain of A joined with drain of B of NMOS, they both are joined together, and they connected with the drain of C input PMOS, so they are connected with PMOS like this. Okay, now the source and drain of input A and B, source and drain of input A and B on the lower side. So this is my source of A and drain of B. They are sharing the same diffusion line. There will be no connection between of metal between them. Similarly, the source of C and source of B, they are sharing the same diffusion. Okay, so the output, let us the output is taken between this. Okay, so similarly, if you consider that we are taking the output from this F point, that is from the drain of the drain interconnection, so then you will take the output, final output from this connection. Okay, so A, B, C are the input, and final output we are taking from here. Now in this circuit you will look at here that there are minimum number of contacts between the diffusion lines. Okay, same diffusion line is used for all the transistors, for all the similar kind of transistors, that is P diffusion, same diffusion line is used for 3 transistors, same N diffusion line is used for 3 transistors. Okay, so in this way we minimize the interconnection between the diffusion. Okay, so that will ultimately reduce the area on the wafer. So that is possible only with the help of the Euler path. So this is a simple circuitry, but if you look at the complex circuitry, and in that complex circuitry you will have to find out first the Euler path by looking at the definition of the Euler path. After analyzing that Euler path, then you will go for actually design of the layout for physical design for that circuit. Okay, thank you.